Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are today at lecture 9. We are discussing about contact mechanics, and in the last few lectures we discussed about distributed load in plane strain approximation on an elastic half space, and we discussed about this distributed load PS and QS. PS is the normal load and QS is the shear load, and we wanted to find out what will be the stress components at this particular point A, which is within this elastic half space at x z coordinate. And we also derived this relation for the deformation gradient for this load conditions, and we have solved some simple problem for this kind of situation. And for example, we have talked about this elastic half space indentation using this rigid punch, and we have discussed about frictionless contact and also with frictional contact. And we have seen that in the case of frictionless contact, this Q is the 0, but when we have friction, then Q does not need to be, if the Q is finite. And so how to solve those problems, how to find out the stress distributions at the contact for this kind of load, that we have seen. So we have also discussed about uniformly distributed normal load on elastic half space, and we have seen the stress components and the deformation at the surface, how it deforms. So that we also did in the last lecture. So we will continue our discussion, and today we will discuss about that indentation using a curved bottom punch. So the bot punch here looks something like this. This is a rigid solid material having this bottom, which can be represented by this kind of equation: z equal to b into x to the power n plus 1, and b is a constant, and let us say that this is symmetric, and so therefore this is n plus 1. This is an even quantity, so it can be 2, 4, 6, but does not need to be what we are discussing here does not restrict to that. It can also be, and n can also be an even number, so that x to the power n, so that n plus 1 is an odd number, so that this particular punch does not look like symmetric, it is an asymmetric. But the simpler case will be an symmetric one. So let us first discuss that, and we will then touch upon that what will be the case when the punch bottom is not symmetric like this. So the punch is long along the y axis, so that we are still working on in the regime of plane strain approximation. So here it looks something like this, that this punch is used to press against this elastic half space, so that it goes by a distance, let us say v at z is equal to v0 at z is equal to 0, that is the maximum displacement that occurs. So this is v at x is equal to 0 and z is equal to 0 is the surface, and at any other x, at any other x, the v is given as the vertical displacement is given as v, and z is equal to 0. So it is a frictionless contact, and we are just pressed using this punch, and so we can write down this v at z is equal to 0. So that is equal to v at 0 at z is equal to 0. So that is this quantity minus this quantity. So minus this z as a function of x, and we know that this is the profile, this defines the profile of this particular punch, and so therefore this is equal to v at 0 at x is equal to 0, and this is z is equal to 0 minus the profile of the punch. I just wrote it as b into x to the power n plus 1, right. So b into x to the power n plus 1, and so here it can be written like this. So del v by del z can be written as, let me write here itself. So del v at z is equal to 0 by del x, that can be written as minus b n plus 1 x to the power n, like that. So here we are writing about the gradient in deformation. So the gradient in deformation is something like this, and we have derived earlier that the del v by del x can be represented like this. So, del v by del x can be 1 minus 2 sigma by 1 plus sigma by e into qx. So, but then qx is equal to 0 here, because this is a frictionless contact, and so therefore, v del v by del x is given as like something like this. And so, here minus 2 into 1 minus sigma square by pi into e into minus a to a p of s x minus s. So, that is given as minus n plus 1 into b x to the power n. So, therefore, p of s, sorry, ds also I should write, dx minus s into ds minus a to a, that can be written as, so minus minus gets cancelled. So, here I will have pi, it is e by 2 into 1 minus sigma square into n plus 1 into b to the power x into x to the power n. So, this is what it can be represented, and so we are getting a general expression over here. So, here p s by x minus s, it comes out to be, we can write it as in this form, g x is equal to a into x to the power n, where a is equal to this particular quantity pi e by 2 into 1 minus sigma square. This quantity we can write it as is equal to a, and so therefore, I have here this general expression over here. Now, here again this is a singular integral, as we can see that s varies from minus a to a. So, at s is equal to x, there is a singularity here. So, there is a singular. So, this kind of integration, there is a general solution for this kind of integration, and so this is can be done and to obtain this pressure distribution function p of x. So, remember that in this particular problem we have we are using the total load p we know, and we are trying to press it. So, we have the vertical deformation, but we do not know what is the pressure distribution at this contact area, and that is what trying to figure out over here, and that can be obtained by solving this particular equation. It seems that this kind of equation has some general solution, which is given by like this over here. So, p of x is equal to minus e into n plus 1 by 2 into 1 minus sigma square, and b a to the power n plus 1 by pi, and I n by square root of s square minus x square, plus capital P by pi into square root of s square minus x square, where I n for n being even and n being odd are also given. So, these are the solutions which are general solutions which are known and done by mathematicians, so we did not worry about it. So, capital X over here is equal to x by a. So, for a given n we can find out what will be this p x using this particular equation over here. So, for odd values of n, the profile of the punch and the pressure distribution is symmetric about the center line, that is z axis, right, that is center line. Okay. So, we can that is there. For even values of n, okay, the solution is something like this. The profile of the punch and the pressure distribution is not symmetric, and so about the center line. So, therefore, it will lead to some eccentricity, and it will also lead to some giving rise to a moment, that also can be calculated. Now, for simplistic situation over here, we will consider, let us say, only n is equal to even, for which the profile is for odd values of n, for which the profile will be symmetric, profile is symmetric, yes, pressure distribution is symmetric. And so, therefore, for the case, let us say for an example, as an example case, that z is equal to bx square, where n is equal to 1. And so, therefore, from this particular expression, I will have here that p of x is equal to minus of e into 2 here into b a square divided by 2 into 1 minus sigma square into pi here, and I of 1 and square root of a square minus x square plus capital P by pi into square root of a square minus x square. Now, at I values at n is equal to 1 can be found out from here. So, see here we have to take only this particular term x capital X square minus 1 by 2, and x to the power 0 is 1. So, I need to take only these two terms. So, here x capital writing x as small x by a, that is the way I will write it, and so therefore, I will have it here minus 2, so at least 2 gets cancelled actually, so I do not need to worry about it. So, I will have minus E b a square by 1 pi into 1 minus sigma square into I 1. So, it is actually given as pi and pi into it is square root of a square minus x square, and this is x by a square minus half plus capital P by pi into square root of a square minus x square, like that. So, if I further simplify this, so it will pi gets cancelled over here, and so I will have here p of x is equal to minus E, and here it is b by 1 minus sigma square, capital B, it will be 1 minus sigma square over here into, here it is x square by x square minus a square by 2. So, here it is x square minus a square by 2 and square root of a square minus x square, right, a square minus x square, a square minus a square plus capital P by pi square root of a square minus x square, like that. So, this is the way the pressure distribution that will look like, and here remember that we are discussing that as if that we have applied this load, and so there is vertical displacement along the z axis, but remember that in the case of adhesion we will have adhesive contact over here. So, therefore, we can have the other way round, that we can apply pulling load over here, and in that particular case it will be, yeah. So, in that case the deformation will be in the opposite side, but then the pressure distribution will look similar that we have done here, and from those pressure distribution analyzing that we will show how to calculate the we will figure out how to estimate the work of adhesion or the energy of adhesion in this kind of problems. So, we will do that, I will take it up and sometime later, but what we are interested now is that what we see here is that in this particular problems, so we can find out the pressure distribution which leading to some kind of parabolic profile, let us say, right. This particular pressure distribution that we obtain, okay, that leads to this kind of parabolic displacement or deformation, or rather opposite way to, so other way to say that we have a cylindrical, we have a punch having this curved surface which leads to this kind of pressure distribution which has P by square root of a square minus a square, like that, this kind of pressure distribution. Now, we figure out a profile that will lead to, let us say, linear kind of pressure distribution. Okay, what I mean by that is that suppose we want to find out a kind of pressure distribution or a kind of punch that will lead to this kind of pressure distribution. So, here the pressure distribution varies linearly. So, P of x is equal to P 0 by a into a minus and mod of x. So, basically, and with a q x is equal to 0. So, let us say we want to figure out a particular type of punch or indenter that will lead to this kind of pressure distribution. So, we will do that using the kind of theory that we just developed. So, for example, over here this pressure distribution is given as P 0 by a into a minus x. So, this profile can be represented by this equation and q x is equal to 0. So, let us say we want to find out what is the total load that is to be applied. So, over here p x into d x, that is all you have to find out, and you have to integrate it over minus a to a. This is easy to do, and what it leads to is this, and this is actually twice of integration from 0 to a into a minus x and comes out to be p 0 into a, that we can easily say from the area of this shaded area as well, okay, is p 0 into a. So, now let us say that for this kind of pressure distribution, what is the stress components at inside at a point x g inside the elastic half space. So, we will follow the process same as we did for the uniform load, and again over here we have this quantity x x is equal to this, okay, this we have already defined like that. So, here this x x can be written as minus 2 z y like that. Now, p x is equal to x minus p s is equal to p 0 into a minus x. So, therefore, this integration needs to be written something like this 2 z by pi, and you go from minus a to 0, and in this regime p s is equal to p 0. So, this value should be negative. So, it will be p 0 by a, and it should be a plus x into x minus s square ds, and over here it is x minus a square plus z square, okay, square like this. And in the other limit from 0 to a, it is p 0 into a minus x, it is a minus x into x minus square, okay, divided by again like this into ds, the same thing. So, we need to find out this both these integrals separately and then add up. So, that is what we are going to do. So, over here we just wrote it, it is like this. So, so let us say that we want to first find out this quantity I 1 is equal to the first integral. So, let us say this quantity, and this is written over here. So, this can be written, this integration can be done here something like this. This is, let us say I will write it here a plus x minus of, this is x minus s, a plus x here into x minus s into x minus s square whole square by into ds, okay, here x minus s square plus z square whole square. So, therefore, this will lead to equal to, this will be a plus x divided by, it is x minus x square plus z square whole square, and it is minus over here, it is minus, this is x minus s cube, and this is square ds like that. So, this is of course ds here. So, this can be represented, can be found out easily. So, this is a plus x into tan inverse this, no, it is square here. So, we have to find it out, no, I will not do shortcut. So, it is like that. So, now let us say this I have done, this much I have done. So, yeah, so x minus s, let us say I will use that z tan theta is equal to minus x minus is equal to z tan theta. So, if I derive it, so minus ds is equal to z sec square theta d theta. So, you substitute over here. So, ds is equal to minus z sec square theta d theta, this is this part, and x minus s whole square. So, that is what z tan theta. So, z comes over here, okay, z square tan square theta. So, similarly, this ds is equal to minus z square. So, this minus and this minus is plus over here, and then x minus is whole cube. So, that is x minus, so that is z tan z cube and tan cube theta, and ds is equal to z sec square theta. So, minus over here, minus minus plus here, and z sec square theta d theta, right, it is like this. And so, therefore, here now further simplify it. So, z cube by z 4 z, so z comes over here in the denominator, and here it is tan square theta sec square theta. So, sec square theta sec 4 theta. So, you get only sec square theta by tan square theta here, and over here you get sec square theta sec 4 theta. So, it is sec square theta here and tan cube theta, and so therefore, here tan square theta by sec square theta. So, sin square theta by cos square theta. So, this is in fact is equal to sin square theta, this is actually equal to sin square theta, and 1 by 2 sin square theta, 1 by 2 sin square theta. So, 1 by 2 into 2 sin square theta, 2 sin square theta is 1 minus cos 2 theta, that is over here. So, therefore, 2 comes over here, and then this term 2 sin square theta becomes 1 minus cos 2 theta into d theta over here, and over here tan cube theta sec square theta. So, here tan cube theta sin cube theta by cos cube theta. So, this sin cube theta over here, and this is cos cube theta. So, cos cube theta and sec square theta, in we get here cos theta, because sec is 1 by cos. So, we get here sin cube theta by cos theta. So, it looks lot of equation, but actually it is quite manageable, as you can see. and so here we have now this. So, now we need to integrate this part and this part is very easy. So, it comes out to be theta minus half of sin 2 theta, that is it. And over here this part, for that we write cos theta is equal to p. So, here minus sin theta d theta is equal to dp, and so therefore, over here it is cos theta is equal to p here. So, p here, and d theta is equal to d theta is sin theta d theta is equal to minus dp. So, minus here, so you are left with 1 sin square theta. So, 1 sin square theta is 1 minus p cos square theta. So, that becomes is equal to 1 minus p square. So, it is like that. Okay. So, therefore, what we have here is in the denominator p here and 1 minus p square here, and since there is a minus sign. So, therefore, this plus becomes minus here, and therefore, finally, we have this equation, and then we integrate it, it will be 1 by p. 1 by p dp is ln of p. So, ln of p is substituted cos theta, ln of cos theta here, and here minus of half sin 2 theta. If we integrate it, minus half sin 2 theta, if we integrate it, it will be cos 2 theta. I think I made a mistake here, 1 by p square, p square, no, that is fine. So, it is 1 by theta, now it is minus. So, this term, let me do it here. So, it is minus, and it is 1 by p minus p dp actually. So, therefore, it will be minus ln of p, which I have written here, ln of p here, and minus plus here, p dp is 1 by, this is p here, p. So, it is p dp is 1 by 2, it is p square. So, p square is cos square theta. So, here minus sign here, and therefore, it is minus plus. So, it is plus here. So, this is fine. So, this sounds good. So, yeah, so we have it, and therefore, we have this integration like that. So, now we can think about that how to write or like here the integration limits are from minus a to a. So, what it means with respect to theta, so that we have to define. So, in order to do that, I have it over here. So, let us say that x minus s is equal to z tan theta, that is the substitution that I had done. So, theta is equal to here tan inverse x minus s by z. So, now at s is equal to minus a, that means s is equal to this particular point minus a, theta is equal to from here x plus a by z. So, x plus a by z. So, x plus a by z, if you see, this is this quantity, this by this. So, this defines this particular angle, tan of this angle, that is pi by 2 minus theta 2. So, tan inverse x plus a by j is pi by 2 minus theta 2, right, like that. And over here at s is equal to 0 is this point. So, I can actually draw a line here and define this angle theta 0. So, theta 0 I can define. So, therefore, it is s is equal to 0 is equal to theta tan inverse x by z, and that will become okay, there this divide this distance divided by this distance. So, that is x by tan inverse x by z, and that is actually this tan of this angle. So, it is pi by 2 minus theta 0. Similarly, at s is equal to a, this is pi by 2 minus theta 1. So, when we find out the limits with respect to theta, okay, so for minus a instead of when you have minus a, okay, I will write this is the limit, and when you have 0, I will write this is the unit, this is the limit, and when you have a, then I will have this unit, this is the limit, that is what we will have. So, this is a very clean way, and so that is what we have done is when you have minus a, I have got actually pi by 2 minus theta 2, and I have 0 here, I have got pi by 2 minus theta 0. Now, I will substitute all this now over here. So, it will be expanded. So, it is minus a plus x by 2z. So, instead of theta I have pi by 2 minus theta 0 and minus this is pi by 2 minus theta 2, this is the way, then minus half, okay, then I have sine 2, this is pi by 2 minus theta 0 minus sine 2, this is pi by 2 minus theta 2. So, this is okay. So, here I can close this bracket, and then minus I have ln of, I will have let us say cos of theta. So, this is pi by 2 minus theta 0 and divided by I can do here directly cos of pi by 2 minus theta 2. And minus plus here. So, it is plus half, this is cos square written. So, it is cos square. So, it is pi by 2 minus theta 0 and minus half cos square, and this is pi by 2 minus theta 2, like this. So, here this we, if we put these limits, it will look something like that, and then it is little more algebra, and that we can easily do. So, for example, this pi by 2 minus pi by 2 gets cancelled over here. So, here we will get minus a plus x by 2 z, and here I will get here theta 2 minus theta 0 here, minus half, and then sin pi my sin, it will be sin 2 pi, so no, sin pi minus theta 0. So, half of sin pi minus pi minus 2 theta 0. So, sin pi minus x is equal to minus sin x, right, that is what it is, right. Sin pi minus x is, no, sin pi minus x is sin x, sorry, it is sin x. So, it is it will be sin, therefore, it is 2 theta 0 minus sin 2 theta 2 over here, and then you can write over here minus ln of, and this is cos of pi by 2 minus theta 0. So, cos pi by 2 minus theta 0, sorry, cos pi is minus, this is sin actually, this is sin theta 0, right. So, it will be sin of theta 0 by sin of theta 2, and then plus it is cos square. So, it is half of cos square is basically pi by 2 minus theta 0. So, it is sin square, it will be sin square theta 0 minus half, it will be sin square theta 2, like that. So, one is to be little bit careful about this theta here, this pi by 2 minus theta and blah blah, but I think it is manageable, one can do that. And so, I have done that, all that, and we get finally this expression that I just wrote there, and then we further we can write it like this. So, using pi by 2 minus, so I have already done all that. So, finally, you have this quantity, we have finally this quantity for this part, okay, this part of the integration. We have to do the other part, so that is over here. So, here I will write it again here little bit the same way that we did here. So, I will write it, let us say a plus x minus, it is let us say x minus x plus sorry about that, it is a we would write a into x minus s, right. So, it is a minus s, a minus x and plus x minus s, okay, and here we write it here x minus s whole square, and this is ds by x minus x square plus z square like this. So, therefore, it will come out to be a minus x integration, here it will be x minus s square by x minus s square plus z square whole square ds plus it will be x minus s whole cube, and again here it is the denominator whatever is there square and ds the way it is there. So, we have to once again to find out this integration and this integration, and we have done something like this earlier, and we can write it like this. So, again we have to substitute these expressions, and that we have done something like this earlier, and finally, we will get here like this after doing all that. So, this kind of thing, similar thing that I did for the other term from minus a to 0 that I did, and now I have this, and then I have to now find out this integration from 0 to a, and therefore, as I said for 0 for the here s is equal to 0 here, for when you write in terms of theta, I will write here pi by 2 minus theta 0, and for a I will write pi by 2 minus theta 1 the way that I have written here. Okay. So, I have substituted here for I is equal to this integration, but I have to just now find out this limits with respect to this limits, and we can find it out finally this expression where we will use this equation after substituting for putting these numbers quantities, and then finally I will have this expression. So, in essence I have therefore x is equal to, we can find out this. So, we will figure out, we will show you that how to do for the zz and the xz also in the next lecture, and I will see also that how to find out the deformation profile, okay, in the at the surface of this film in the next lecture, okay, surface of the elastic half space in the next lecture. So, thank you for your kind attention.